اوكي. بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Assalamu alaikum everyone. Today, inshallah, will be the last lecture about the math part. So pure math part. So we still have the math till the end of the course, but at least today will be the last lecture where you're gonna be given more tools, hopefully with some teasers in the end to show you really how this stuff, will be used in the future. But starting from next lecture, inshallah, you're gonna be seeing physical stuff. Okay. Still, we're going to be representing them in mathematics, but at least everything we discuss from now on, starting next lecture, will have a physical meaning. And we'll be using the tools that we learned so far in the course, inshallah. So let's start with a recap. As usual, before I start, so the vector spaces 3 lecture. So this was actually not in the previous course. So this was a new material. Well, it was like an extended version of what we discussed earlier in the previous course. And this also material, you're not gonna find there's a second lecture for the Lie groups and manifolds. However, you'll find that actually this is still an expanded version of it. And it also some of the material that was here was in the previous course given within the the physical part, within the robotic stuff. So here we just like collected them and giving you like again like one extra lecture where you have this abstract notion and all of these concepts. And then later we're going to be seeing that when we come to the physical part and the robotic stuff, we're going to have to recap these definitions, okay, and these concepts, but you'll be more familiar with them. You'll be more comfortable actually just trying to understand how they are. So having that said, try to understand the concepts that we discussed today without any physical notions, just abstractly. If you understand the concept, then you're good to go and move on. So yes. No, I uploaded it. Solution of homework 1 is already online. Yeah. So always send me. Don't wait till the lecture. If I don't upload the stuff in time, just send me a message. Unfortunately, the new version of Blackboard doesn't give you a notification whenever I do it. I'm still trying to figure out if have you seen anyone in other course doing that you get a notification once it's uploaded? That's right. At the end of the day, exactly. But you don't get these individual ones. Okay, cannot help it, unfortunately. I enjoyed the previous one, honestly. Okay, I did not receive any of these notifications, but you're getting all of the spam. But at least you are still up to date. So for now, I think you can always keep up with the notifications board. If you download the app of Blackboard, you will find it. You can also get notifications. I think it's something that you need to play around and check with your colleagues. Today, we're going to be looking at new concepts, which is the tangent space of a manifold, the cotangent space of a manifold, and what's known as the matrix Lie groups. And hopefully, we're going to be able to cover all of that material today, inshallah. Recap. Rn from now on, okay, hopefully after the course, you're going to be looking at it differently. Okay, you're not just going to think of Rn as, the set of all vectors that I can do everything with. You're going to be always thinking about which structure you're talking about, whether you're talking about Rn the set, which is just the Cartesian product of R with itself n times, or as a group, when you take 2 vectors and you add them together and you just get another vector in the Rn, or as a vector space, when you even have more stuff than just, adding them together and having the additive inverse. You can start to, having a field and concept of vector space over a field, and you do more stuff. Related to that is something which is the inner product, which we didn't discuss, but it naturally follows from a vector space. It's an additional structure to a vector space, which is, you take an inner product between 2 vectors and you do more stuff. As a manifold, which is the last time, and usually you need to think of Rn as a manifold when you want to discuss differential equations, when you want to describe there is some sort of curve of something that's, not just a point abstractly, but we have something that's moving, we have something that there's some sort of change with respect to time. And because you have change with respect to, then you're talking about, continuity and differentiability, and you need to differentiate, what you're talking about. This is all what you had earlier in calculus, all of the calculus that you know how to do in vector calculus with Rn. This is usually, you've assumed that you have that structure. So any set that you give it this differentiable structure, which is related to this idea of being able to talk about continuous maps and differentiable maps and so on, then we call this a differentiable manifold. And we said that this this is just an informal, intuitive introduction to, differential geometry and to manifolds. You need to, we need much more time just to properly, introduce that subject. The fundamental object of differential geometry is what's known as a differentiable manifold. You can intuitively think of it as, if you have an n-dimensional manifold, then it's a set that locally looks like an open subset of Euclidean space Rn. And we have an example, which is the circle S1, which is you see it as a surface in R2. If you have the sphere, the two-sphere, okay, which is simply a surface in R3. If you have the torus, it's a two-dimensional surface in R3. And you have space-time, okay, it's just a four-dimensional surface. And this is funny enough that, okay, that you might think, okay, but what is space-time embedded in, right? So you think about, do I always need to think of, like a bigger space where this is placed in? Okay, this has some deep mathematics, answer to that if you want, we can discuss after the lecture, if you're interested about that. Always keep in mind, because this will come up again and again in the remainder of the course, is that in general, a manifold does not have a vector space structure, which means that any 2 points there, I cannot take the sum or multiply it by a scalar. It's not defined. And also, it might not have a group structure, which means that I might not have a binary operation that takes 2 points on the manifold and gives me another one, and so on and so forth. There are special types of manifolds that do have this group structure, and we give them the name Lie groups. And this will appear a lot. Okay? They appear a lot in robotics. Okay, but not everything that appears in robotics is just a Lie group. We usually have these more nastier objects, which are just a manifold without the group structure. Yeah. Any question? Okay. This is just a quick recap of what we discussed last time. We said that in order to talk about a manifold, we need to give it this idea of what a topology, and we need to start talking about charts and the atlas, and we'll give this intuition using the atlas of the world. Actually, it's the same ideas that actually even the same names were inspired by it. So if you have a manifold, and you imagine this manifold usually as some sort of curved surface in a higher dimension that we're gonna have a lot of these pictures, but sometimes we're thinking about a three-dimensional or a six-dimensional surface, which is you cannot visualize. But usually this is just the abstract picture where the manifold is just some curved surface. If you take some domain on it, and then you can map it with a chart to a piece of Rn, which is an open subset at Rn, and you can have another chart which goes to Rn, and so on. So we call this pair of phi and u, we call it a chart. And if you take the collection of all of the charts that in the end would cover the whole manifold, we call this an atlas. And it's very important to identify that all of these charts, how are they defined, about the differentiability. So we talked about last time about functions of class Ck. So class C0 would be continuous functions, C1 are differentiable functions, of order 1. C infinity would be, nope, infinitely differentiable functions, okay? There's like smooth, and there's just a famous name, it's just smooth functions, exactly. So smooth functions in the end would have C infinity, class C infinity. And these are usually maps from Rn to Rn, or from R to, from Rn to R. You can just, you can take all of these functions, think of them individually. And if we have all of the maps that go from each chart to each other, from one chart to the other in the overlap region, they need to be, compatible with each other. So this compatibility is usually in the end by this class Ck. So whenever we say I have a smooth manifold, this means that it's like it's a surface where I can always represent it by charts that I can talk about, moving from one chart to the other in a smooth way. So there's no loss of information, there's no loss of degrees when you differentiate and stuff like this. This is a very abstract notion, and once we start working with stuff, so that's actually some point to mention here. So when the extra structure we gave to a set being a group or a vector space, we had stuff to work with, right? You had, this idea of operations where I take 2 points and I compute the addition or the multiplication and so on and so forth. But when you have a manifold, you don't have the extra structures like embedded inside. We don't explicitly talk about it. But whenever we're differentiating with respect to time, we need to have the structure. So always think about it like this. Whenever we have like something that has differentiation with respect to time, then you already need to introduce this idea of differentiability. No. Don't confuse stuff. Lie groups, you mean? Lie groups. Yeah. Okay.
Binary operations.
Lie groups are a manifold and a group. So you can have groups without talking about differentiability. But if you have a group and you're starting to talk about, I have a curve on this group and I'm going to be taking the differentiation with respect to, some parameter, then you're already talking about topology and, differentiability and stuff like this.
Then have a manifold that's differentiable.
I'm not going to go to what ifs. Okay. So you leave the what ifs for later on. Okay. So the answer is usually yes and no, and you need, to give you to so many examples. So don't think it like this, okay? Just take the abstract concepts as they are. Stop with the what ifs, okay? That's for everyone else, okay? Don't overload your mind, okay? This is already too much. We discussed last time the idea of a curve on a manifold. So a curve on a manifold is simply a map from an interval, okay? And this interval is just a subset of R to the manifold itself. And visually is exactly what you see there in the red curve. All of the notions we're using are exactly what you see there visually. So the curve is simply just a map from I to M. So this I, it can be an interval, from 0 to 1, from A to B. It can be open, it can be closed. It's not important. So here, for example, in this idea, when we say that interval is just a closed subset from A to B, then gamma at A, okay, is a point on the manifold. Gamma at B is another point on the manifold. We call this x1 and x2. So this is what we have here. Then we introduce another notion, which is maps between manifolds. Okay, so we can have a manifold M with its own differentiable structure, and then we have a manifold N with its own differentiable structure. So a map here called X will be mapped there to another point. Sorry, a point here called X will be mapped to another point here called X tilde. Okay, so x1 here will be x1 tilde here, x2 here will be x2 tilde, and so on and so forth. You go from M to N by F, you go from N to M by F inverse. It's not always the case that they have the inverse. If it is the case that you have a function that's smooth, infinitely smooth, so it's infinitely differentiable, and you have N inverse, it exists and it's also infinitely differentiable, what do we call this F? Nope. Diffeomorphism, exactly. We called it
Should they be a Lie group?
No, that's a good question. So should the manifolds here be Lie groups? No, not at all. They can be just, manifolds without a group structure, and you can still define all of this concept. If you have the Lie group structure, which means that things become more interesting, and this is exactly what we're going to be seeing. I don't think today, but hopefully next week, inshallah. Okay, but keep that in mind. Okay, whenever you have more structure, things get more interesting. You can introduce more stuff and you can do more with it than just stuff that doesn't have this extra structure. There is a special case of this where N is equal to R, and we call this maps on the manifold. So a map on the manifold is simply just a function that goes from M to R. Okay, so X tilde here will not be just another manifold. It is another manifold, but this is just in a one-dimensional manifold, the simple case. Sorry, what the word, is it like projection? I don't know, because the word projection itself has meaning. Okay, when you start talking about differential geometry, so don't confuse the terminology. What we're introducing here is terminology. So so later on, whenever you hear a map on the manifold, this is the picture that's going to and so on and so forth. Okay. So this is the picture of the manifold, and the map F here will take you to R. So that's the idea. And then we had this notion that we say that F, this map itself, belongs to Ck of M. So this was the notion. So Ck of M is the set of all maps that go from M to R. So if I take any element from there, it's just a map that goes from M to R. And the key simply was to identify its regularity. It's like degree of differentiability. Whenever we say it's C0, this means it's just a continuous function. If it's C infinity, then it's a smooth function and you have everything in between. But it's the notion itself, if I have a map on the manifold, we did not introduce, we don't know how to describe differentiability on the manifold. And this is the whole idea of the charts that we discussed last time. So for every F, we can define what's known as the local representative of it, if you remember from the chart. So the chart takes me from M to Rn, and because I have a map from M to R, I can define a new map that goes from Rn to R. And from Rn to R, This is the normal calculus that you know. So I can always do differentiability there. I can talk about something that's of a class CK, and then we just lift the notion to the manifold. This drill I just made right now, you're gonna find it again and again. If you read in differential geometry, it's just something that's repetitive, right? We define stuff in the chart, okay, because we know how to work with Rn, and then we pull it back. You know, we take this concept and we just say, okay, this is how the manifold behaves. Okay, we always do that. I'm gonna have another example in a bit, inshallah. Yes. Sorry? Camera is not plugged in. Why are you saying that? Because of this. No, this is just an adapter. Okay. You give me a heart attack, okay. No, this is just an adapter from USB-C to USB. Thank you very much. Okay. Don't do it again, okay? Sorry, yeah. Sorry? To R2, you mean? Yeah. Think of R2 as another manifold, and you define the same here. So this was a special case. Maps between manifolds, yes, you can from any manifold to any manifold. They don't have to be the same dimension. Okay, so this can be from R, something that locally looks like Rn, which is n-dimensional. So we have an n-dimensional manifold to a m-dimensional manifold, or you know what I mean, right? Yes.
Are charts same as maps between manifolds? Can I say it's the same?
It's a special case, yes. So if you think of Rn as a manifold, okay, so if we go back here, so a chart, okay, will take you from M to Rn. Okay, if you think of Rn itself as a manifold with the standard topology that it has, which is whenever I say standard topology, this is what you took in math. I don't know which course, you know, just working with Rn, you know, the standard stuff that you do there. So yes, you can think of it, yes, as a special case. Yeah. So now we're going to be using another abstract notion, okay, another geometric object, which is very important, which is the tangent space of a manifold. This is how it starts. Actually, there was something in the figures here, and I was hoping someone would ask, but no one did. So yeah, the arrows, the red arrows. What is the V, right? Intuitively, if you look at it, what comes into your mind about this V? Tangent, yeah? Tangent what? Tangent what? Tangent velocity, tangent to the trajectory. That's exactly what it is. It's a tangent vector to the curve. It's exactly intuitively what you have in mind, and this is just the formal definition of it. So consider that we have a smooth curve, you know, because we're going to be taking differentiations now. We need to, identify which class are we talking about. Is it C1 or C2 and so on? From now on, everything is smooth, right? So everything is C infinity. We can take differentiation as many as we want, and everything remains. When we differentiate something that's smooth, it remains also smooth, and so on and so forth. Consider a smooth curve, gamma that goes from some interval to m. So how is it defined? It will eat any t. The t here is just a parameter. It could be time. It could be something else. It's just a parameter. Then it eats it and it spits out a point in the manifold M. So gamma of t is a point, and t is just a parameter. Something goes from 0 to 1, from A to B, just some parameter. Yes, exactly. The curve is always, I don't know what you mean by one dimension, but if you mean that the domain itself is one dimension, yes, that's true. Yeah, it's always a function of one parameter if you think about it this way. Yes. So this is the definition. Stop with the what ifs, okay? The codomain here is n-dimensional. M could be n-dimensional. We haven't talked about the V yet. Wait. So this is only the curve itself, the blue part. Okay? So it's something that, you give it a t, it will give you a point on the map. So in the end, it's just a collection of points. The point on the map is an abstract object. If you take a chart and you look what it looks like, you can represent it with n numbers. So yes, so it is n numbers, only the chart. But on the manifold is just an abstract concept. If we differentiate with respect to the curve parameter t, we get the notion of what's known as exactly what you described, the tangent vector to the curve gamma. But here is something missing, because you always need to define the tangent curve to the curve gamma at the point exactly. You have to define at some point. That's why you see here, for example, v is defined at x1. If we look at the tangent of the vector at x2, we're going to get another vector and so on. Okay. So to be precise, if gamma of 0 is equal to x1, then v is simply the differentiation at t equals 0. Exactly. So this is a tangent vector at the point x1 m to the curve gamma. Any questions? So exactly what you said intuitively, I wrote it, in words. There should be no difference. How do we define the direction of the vector? It will follow naturally along the curve. It's like in the direction where the curve will change next. But the proper question should have been, how do we define the derivative of a function on the manifold? Right? Because if we don't know, the manifold is something abstract, right? How can we define differentiation with respect to something? And this is where the same idea that I just told, go to the curve, go to the chart, and you know how to define differentiations. So gamma itself, okay, I can take, because it's a collection of points here that that are in the manifold, and every point on the manifold, I can go to a chart in Rn. So we can always, so phi here will eat, the curve and will give you a number of points on Rn. So in the end, if you look at the circ of phi and gamma, you have a curve that goes from R to Rn. Okay? So it's like just, if I draw a line like this in R3, this is simply, a collection of points. You see points, which in the end make a curve, but you see it in R3, right? I can take the curve and I draw something like this, right? It's another curve in R3. This is a curve in R3 also, but it's just, it's just a line, exactly, and so on and so forth. So this is exactly what we have here. And this is what you know how to differentiate. Okay, if you go back to your normal calculus, you find that this is it's trivial, right? Just simple math, taking the differentiation with respect to time. So it's just like you have a function of only one parameter. How do you take the differentiation? You know exactly how to do it. So there's no magic here. But after you define that, this is exactly what we mean here by the gamma, abstractly. No, the image is something in Rn. But it's in Rn.
Can't say it is one-dimensional in the Rn.
It is a one-dimensional manifold in Rn. No, the image, yes, yeah, the image of it exactly, yeah, absolutely, you're right. So the codomain itself is all Rn, but if you only follow the points where the curve is mapped, it is actually the manifold itself, yeah. But be aware, now we're going to be confusing how the curve looks like in numbers with the abstract curve itself. So gamma is the curve itself, pi after gamma is how it looks in Rn, okay? Because it depends on the choice of the chart. Now let's do something. So a question to you. If I look at the direction V, okay, how many V's do I have? You can have infinite number of V's, right? Because you can move in many directions in general. Of course, to this curve, you have only one V because you're moving, with one speed. But if you look at this point, it can have many, in general, because it can have many curves, you can have many V's and so on. And even this V can be this long or this long and so on and so forth. It can point to the other direction. Okay. In the end, they just make what's known as a tangent space. The V is a vector, so it has to live in a vector space. The vector space that collects all of the V's is simply known as the tangent space. And this is its notion. So the tangent space Txm at a point x in M is the space of all possible instantaneous directions you can move from x. In general, not just to this curve. Okay? So it's not just the curve here that you see there. Okay, assuming that it has some parameter, then it gives us the red curve, the red direction there. But in general, if you look at all of the directions possible, you have this, image of this space that's, from its name, it's tangent to the manifold itself.
follow the plane?
That's a good question. Let me go to the example, and hopefully it will be clear. Ask that question again, okay, if it's not clear. Let's take an example, okay? Let's take two manifolds, one which is one-dimensional in R2, and another one is two-dimensional in R3. Okay? And let's look at, visually what does this idea of tangent spaces looks like. Nope. So at this point here on the top, okay, no, cancel. Yeah. So the first thing we need to have, this is the abstract picture, remember it? Okay, so this was the manifold. Now we have two examples of manifold. And then we had a curve on the manifold. And then a point here, okay, had this idea of the V. And the point itself, we called it X. Clear? So this curve itself, how does it look like? If this was the point X, which was the point at which the curve was equal to 0. So for example, here, gamma of 0 was equal to X. So this is where it starts. Okay. By the way, the time parameter, you can always shift it, right? I can make the 0, 1, and the -1 will become the new 0, and so on and so forth. So X here is exactly where the curve was there. And then it moves like this. Let's say, for example, we stop here, and this is, X2. So this is X1, and this is X2. So this is X1, and this is the point X2. Clear? So that's clear? Now the tangent vectors themselves, I'm gonna draw them in blue here so that you see them. So the vector itself, if I'm here and I'm moving along the circle, what is my direction? If I'm here, upwards, exactly. I'm just upwards. This is my direction. So this is V, the tangent to the curve at the point X1. If I continue moving on and I come to the point X2, and I'm going to continue moving in the same direction. But let's assume that here I was moving, fast, and here I'm going to be moving even faster. I'm just, going to speed up down the hill. What would be the direction of V? Also tangent, but it will be bigger. Exactly. So let's have a new curve, where, for example, we're going to reverse it. I'm going to start from X2 and I'm going to go to X1, but I'm going to go very fast, and then I'm going to be going very slow. So in the end, the direction would be like this, and then here would be something like this is very big, and this is very small, and so on and so forth. Okay. So you see the idea that this is the point, and this is I give you, two, or we can think of, more curves, like a set of all possible curves. In the end, they all will belong to this line, while this curve, all of the vectors here will belong to that line. So you see this line here, we can simply call it T, X2 to the manifold, and we're talking about a certain manifold S1. Okay, so this should be the double S1. And this line is simply Tx1 with the manifold S1. And so on and so forth. We can take any other point, and we can do exactly the same. You're just going to, the picture will just become, unbearable. Yes?
So just can comment. For each point, it has its own tangent space, and it should be all of the points that you can reach using the vectors on.
All the points you can reach. Where are the points there?
Let's say all the tangents that is possible to reach on this point here.
So if you're at this point, the space, which is the tangent space, is the collection of all possible tangent vectors, tangent directions that you can move in. So I can move, very small, can move very fast, I can move this direction, and so on. Here, how many directions can I move in? No, one. No. I can only move in one direction here. Up and down. What is up and down? It's the same direction, but with what? With the negative axis, right? One is positive, one is negative, and what? So R is one dimensional, right? But R has positive and negative, so it's one dimensional. But you have positive numbers and negative numbers because it's a vector space, right? So here, it's only one dimensional. So you see here, the dimension of this one is equal to 1. The dimension of that space is also equal to 1. Are they the same space? No. Can you take a vector here and sum it to a vector there?
Vector?
Can I take a vector from this vector space? Sum it to another vector from a different vector space? Summing vectors. Can we do summing vectors? Yes, of course we can sum vectors. Can we sum vectors from different vector spaces? Of course not. They're not defined. You cannot sum vectors to the vector. I'll give you an example. I explained to you now what does this direction mean, right? So I'll give you two directions in yellow now. What is the sum of this direction and that direction? What does it mean physically? Nothing.
On the manifold, it's going to be like this, one like this.
That's exactly what you have here. Yeah, but that's exactly what you have here. This is a manifold, and this is exactly what you have. So again, so for example, if this is how this V looks like, this is, for example, how the other V looks like. So this is V at x1, and this is V at x2. This means you cannot sum them because they live in different spaces.
It's not over this axis. We can only take two elements from the subset up and down, not all. And we cannot move up forever and down forever. So it is not one
At instantaneously. How many? What can you do? But no. But you can go twice as fast, or 2.5 times as fast, or half as fast, and so on. That's why you have a whole vector space.
If we define this is in the region of epsilon.
No. It's as exactly what we said. You don't need to talk about epsilons or anything. Yeah. Infinitesimally, yes. Yeah. So what you're saying is correct. Yeah. Infinitesimally motion like this, but but you're going to be thinking about that. Actually, I'm going to be moving outside of the manifold, and then I'm going to say infinitesimally how that goes. But what I just drew here actually makes sense intrinsically. Intrinsically means that without thinking about this being in R2, just on the manifold itself. Imagine that you have an ant that never leaves the manifold. This is usually the visualization.
Wouldn't that mean I have to sum these vectors?
That's an excellent question. So what if I have something that needs actually to calculate, some vector here minus or plus some vector here? Can we do that? In general, not, unless you use some extra machinery that does that.
That has these.
Maybe a kernel?
No?
That relates this vector space with that.
Exactly. We're going to be introducing something, okay, that will relate this vector space to that vector space. What this something is known as is it's called a connection. It's related to something called the covariant derivative. It's related to something called Christopher symbols. If you ever seen something like this, it's related to this. And it's also something that appears in robotics, but something. The kernel is something else. The kernel is something different. Okay, yes.
So with that dimension of the tangent space is the same as the dimension.
That's a good question. Is dimension of the tangent space at any point of the manifold always equal to the dimension of the manifold itself? The answer is yes. Always the case. Yeah. Another example. So let's go to another picture. So how would a curve, so the same abstract picture, I'm just going to draw it on a different manifold. So this is, imagine that you take your car and you take a very long trip. You start at the North Pole, okay, and you go, I don't know, go up to where, okay, but maybe something in here. I don't know where, Egypt or something, okay? So this is where X1 is. This is where X2 is. And you have, if you're in this point, how many directions can you move in on the sphere? How many directions? Only two, right? You only need two directions. For example, you can say that one direction is like this, and the other is like that. They have to be independent, which will give us the notion of what? The basis, exactly. Two directions, E1 and E2. In the end, if you take the span of these two, you get what is the tangent space to x1 at the manifold S2. It looks like what here? It looks like R2, exactly. And this one, what does it look like? It looks actually, this is isomorphic to R, and this is actually isomorphic to R2. Yes.
Like, can it be planar as well? So we will call it tangent even if it is a planar?
I don't, even if the manifold itself is planar. Yes, but it will do some confusion now, but leave it for later. Yes, even if the manifold itself, I think the word you're looking for is flat. If the manifold itself is flat, you still have the notion of a vector space at every point. This is something we're going to be looking at in the next lecture, but don't think about it right now. It's easier to think about, like this for now. But what you said is true, yes. So this is how this tangent space looks like. This is how this tangent space looks like, and so on and so forth. The dimension of this is equal to the dimension of the manifold. So the manifold was two-dimensional, and the dimension of this tangent space at this point and that point and any other point was also 2. Okay, yes.
Other than this in the past.
Like what? So here you're thinking about differentiability, right? So I need to move in one direction, right? If you come at one point and you move in this direction and that direction, have you ever seen something like this physically? So that's why we're thinking about physical. We're gonna start to think about physical stuff here, right? Sorry?
Space is contingent on a manifold.
Con?
A tangent space can only exist with the existence of a manifold.
The tangent space itself is a vector space. Okay. So defining it by itself as the set of vectors, yes, we already discussed the vector space on itself. But all of the vectors when we discussed the abstract vector space did not have a meaning. Here the vectors, they have a meaning. So this is why it's called the tangent space to a manifold. Okay.
Is for what? As a set
as a vector space. This is as a vector space, yeah. So this is isomorphic to it as a vector space. And this is actually what you see already. Visually, you can already see that it is true. It is actually.
that manifold is just a theoretical thing.
Next lecture. Wait, leave that to the next section, okay? We'll come to the idea of a flat manifold next time. Actually, if you want to think about a flat manifold it's actually Rn. Whenever you have Rn and you have a curve in it and you start to do differentiation, you're thinking about Rn as a manifold that's flat. But we didn't. Flat is something intuitive. We did not introduce it formally, because to introduce it formally, we need to think about curvature and we need to go into more complicated stuff. So let me give you an intuition. It will even I don't know whether it will mess with your mind or not. But space-time, which what we live in, is actually a curved manifold. So it is a fourth-dimensional curved manifold. So okay, so I don't know if that makes sense or not to you, but it is it's proven experimentally. Okay. So let's see. Let me take this picture. Let me save it. This PDF.
It is a shaft, right?
Sorry.
This is it is a shaft.
No. This has nothing to do with charts now. No. The manifold itself has a vector space associated to every point called the tangent space. The chart was something else. Was when you take a patch from here and I want to describe it in coordinates, then we have the chart. So in other words, that's actually a good point. So charts describe points on the manifold with Rn. But vectors, but the tangent space describes, which is related to, what is the word? If these are points or positions, these will be instantaneous change of the position, which is related to the velocity. It's not the velocity, it's related to the velocity. This will make sense later. Absolutely. That's the correct way to say it. And we're gonna look at it in a bit, inshallah. Yes.
That why we have the tangent space always relevant of R n. It's not really
Like this, that's a good question. Why do we have that this vector space is always isomorphic to R2 or Rn? You remember the theorem we said that every finite dimensional vector space is actually isomorphic to Rn? That's exactly what you see here visually. Okay. So if you give me any vector space abstractly, because we can start talking about bases, we can always go to numbers. That's exactly what we did here. I talked about the bases, then we took this abstract notion, you already saw numbers. You already saw X direction, Y direction, and so on and so forth. So we need to stop, not with the lecture, but with this part. Let's move on. Okay, now how much time do we have? Okay, nice. Now I'm gonna go a little bit fast, okay? Because you got the idea, you got the intuition. Let me just bombard you with a number of concepts that they all make sense abstractly, but with numbers, don't try to think about them as numbers. The first thing is what's known as the tangent bundle. The tangent bundle is simply take all of the tangent spaces and put them in one object. You get the tangent bundle. So the tangent bundle is defined as the disjoint union of all of the tangent spaces on all points on the manifold. That's it. If I take a point here in this set, what do I get? I get a pair, a P and a V. The P is the point on the manifold, and the V is simply a vector in the tangent space on the manifold. So this is what a disjoint union means. Okay, so I'm not just taking M, so I'm not just taking all of the vectors, I'm also taking each point that it comes with. You know why? Because every tangent space, I need to know where does it belong to, right? I cannot just give you, T, I cannot just give you this plane. You have to always ask me, is this belonging to X1 or X2 or X3 or X4 and so on and so forth. This is why, we make the tangent bundle like this. The tangent bundle itself is a manifold. If dimension of M is n, then dimension of this tangent bundle is twice of n. So you remember what we said about the manifold? It's something that locally looks like Rn. So now the tangent bundle will locally look like Rn times Rn, right? So it will have Q's and Q dots, whatever that means, but keep it for later. And this is very important in Lagrangian mechanics. If you ever did Euler-Lagrange equation, you've always worked with this without knowing. Okay. Another concept, very quickly. It is related, of course, to that. Yes. Yeah. Yes. Then why the torus?
Because I think each point will have multiple tangent spaces.
No, every point will have one tangent space. They will be very close to each other. The torus will look nothing else than just this one. Right? It will look like it's another surface in 2D. So exactly what we drew here, we can do for the torus. Look at every point and look at the tangent space and draw the same circle. But if I take the tangent space here and this point, they'll be very close to each other. So, but every point has only one tangent space. Clear? Because a vector space is, a tangent space is what kind of structure does it have? A vector space. Whenever you have a vector space, you have what always comes with one vector space? No, not the dot product. No. The duality, exactly. So if we have something called a tangent space, okay, then we have something called a cotangent space. If the tangent space is the space of all possible instantaneous directions between, brackets velocities that we can move from X, and we said that this is an n-dimensional vector space, then the cotangent space, which we write it like this. You remember we introduced the notion that V and V star a more common notation for, instead of just writing T, X, M, and then putting some sort of bracket and writing the star, is actually writing the star like this. So this is what we're going to be denoting the cotangent space of the manifold. It's simply the set, or the space in this case, of all linear maps on TXM. So if you take any element in this cotangent space, what do you get? A linear map that will eat the vector in this vector space and give you a real number. That's it. How many cotangent spaces do we have? For each point, we have one vector space, one cotangent space. What can we do? Can also take all of these cotangent spaces, put them in one big, object, and we call this the cotangent bundle. Exactly. So the cotangent bundle is simply the pair of every x and every linear map, where the x is a point and the linear map is simply a covector. It's a smooth manifold on itself. And if this is dimension n, then this is dimension 2n. And simply it looks like Rn with Rn star. You remember what we said about, Rn star and its relation to Rn? Okay? That Rn simply changes coordinates differently from Rn star. You have the homework number 2. You're going to be seeing this clearly with numbers, with vectors. We had an example in the lecture where we said Rn, okay, would change coordinates, with some matrix, but Rn star would change coordinates with the transpose of this matrix. If you go back to the lecture we discussed. Yes.
The bundle is points and a vector or a tangent space.
The word bundle itself as a mathematical object can be something, more complicated than this. So we need to introduce it formally. But if you take not just the pair, and this is, this is very important. It's not just taking, this point and this element. No, this is the formal definition of it. You take all of the tangent spaces and you take the points that come with them and you put them in one set. And this set, defined like this, will have a manifold of its own, and have a structure of its own. You can actually define charts for it and so on and so forth. Okay. So if you take a point here, you get this pair. So it's not the other way around, if that's your question. We don't make up the cotangent bundle by taking every x and every element. No, you just take the, in this form. And this is why it's called a bundle. Okay, but it's actually much more deeper than this, because bundle appears a lot and it's something, very, very important in mechanics. Okay. But these are only 2 examples of bundles, so maybe that will answer your question. So you can have many bundles. These are only 2 types. I give you an example of the tangent bundle and the cotangent bundle. And this is how they are formed like this. Okay? And where does this play an extremely important role in what's known as Hamiltonian mechanics? If you has anyone heard about Hamilton's equation? Q dot is equal to gradient of H with respect to P, and P dot is equal to minus the gradient of H with respect to Q. It's used in optimal control, that's right. And it's used in a lot of stuff. This is related to working in this direction.
The cotangent space should always share the same manifold with its tangent space.
Yes. Yeah, because it's defined as maps that eat vectors from that space. So for example, if I tell you alpha lives in V star, where should it only eat? What should it only eat? Elements from V, to give you a real number. Can it eat something from W? No. So that's why you see every cotangent space has its own tangent space, and every tangent space comes with a point, and every point lives on the manifold. So they're all concepts connected to each other. This is just the notation. This is just notation. Okay, to be proper, in order to follow the same stuff we did earlier, we should have called this, something like we should have called this something like TXM all star. But it's too heavy notation, right? So it's just simply take the star inside and remove all of the brackets. This is just notation stuff. Okay. Let me just. Sorry?
Set M itself can be.
That's a very good question. Well, that's a typical exam question. Okay, so can M have a dual? So what is the M star? Is it defined? Yes or no? Should be the dual of the manifold, right? Makes sense, right? If I have a dual of V, I can have a dual of the M. Exactly. See, now, so don't think about them as just symbols. There's a lot of mathematical structure now. You remember what we said? If I have Rn as a group, it's not the same as Rn as a vector space. It's not the same as Rn as a manifold, and so on. So here, being a manifold, there is no such thing as the dual of a manifold. Okay. Exactly. Duality is only for vector space. Every notion we introduced, always think about what structure we were talking about. For example, linear maps, there is no such thing as a linear map on a manifold, which is a huge mistake. You find this a lot. You say, I have a space, which is a manifold, and I have a linear map on it. But what does linear mean? Linear means you should have an underlying, vector space. You're going to see this again and again throughout the course, hopefully, inshallah. Absolutely, yes. The tangent space is a vector space, and that's why it has a dual. Any question? Okay, so let's go back. Yeah, there is one example of a covector that's extremely important, and we're going to be using it later to do control. Okay, this will not make any sense now because why we're not going to be using it now except after the midterm even. So, but when you come back to this, you find that, okay, yes, now it makes sense. But that now is some many weeks from now. But try to understand it as is. A very important example of a covector is what's known as the differential of a function. If you give me any function on the manifold, if it's smooth, then at every point, we can define what's known as the differential of that function. So the differential of the function, this is the notation of it. It's df, and it's at a point x. So it's df at a point x. Where does this live? It's a covector in the cotangent space to the manifold M at the point x. It is defined such that if you give me any vector v, can this covector eat it? If you give me any vector v that lives in Txm, can this covector eat it? Who's saying no? This is a vector, and this is a covector in the dual space to that vector space. Can you take this covector and let it eat this vector? Yes, of course. Yeah, just like the alpha eating the v. This is the alpha, and this is the v. What do you get in the end? A real number. Exactly. What is the meaning of this real number? It's actually the directional derivative of f at x along v. Who heard about the directional derivative before? Okay. You all heard about it. Okay. And this is usually how you think about it. Okay. Or at least you know it mathematically. It's actually the gradient of the function f. If I give you a function, I tell you calculate the gradient, you can calculate it. Just partial derivative of f with respect to x1, partial derivative of f with respect to x2, and so on and so forth. If I give you two functions, f eat after g, I tell you take the chain rule, you take f by partial f by partial. It's a fancy. You use it all the time, and it's actually related to this idea of the differential. Looking like this, you remember what we said before? Does anyone remember when we said that alpha transpose v? Remember, alpha written as a column vector and v written as a column vector, and you take the transpose between them. And you said the dot product back then. I told you there's no such thing as a dot product. Why? The dot product is an inner product, but the inner product is always between what? The same two vectors in the same vector space. Looking like this, if I tell you that df of x is a covector, so they're not in the same vector space. So if this changes coordinates, this will change coordinates differently. So the gradient that, if you have, partial f by partial x, have you ever seen some people write it like row vectors, and some people write it like column vectors? all of this, you know, once you go back to, my suggestion is the following. Go to the first time where you saw in your math courses the partial f by partial x1, partial f by partial x2, and so on, and see what did you do there. Okay, you're gonna 100% see that you wrote it as a vector. This is an example of something. You think of it as a vector, but in fact it's actually a covector. It's a covector. You write it as a column, you write it as a row, it doesn't matter. It is that. That is the gradient. It's not a vector. It's a covector. Absolutely. Why is it a covector? It's simply because it is a covector. Very good question. Change coordinates and see what happens. The same what we did, you remember, did you attend the lecture when we had the alpha and the v and we took the columns? Did you do homework 2? Go do homework 2 and then you're going to see, okay. Do homework 2 first, come back to this, and try to look at, your exercise should be the following. Try to represent, take a function of some variables, of some x and y and z, Cartesian coordinates. And then here, calculate the differentiation of that function with respect to dot. And then calculate the gradient of that function with respect to x and y and z. Now, try to represent this as polar coordinates and see what happens. Okay. We're working on something. Okay. I wanted to give you as an assignment or as a homework, but it will be too much. Okay. So I'll give it to you written in some sort of in the lecture notes. Okay. So inshallah, we're going to be working on some lecture notes. You're going to be given some stuff, you know, to read as more reading material. You're going to find this example of how does this change coordinates, how vectors and covectors change from Cartesian to cylindrical coordinates or polar coordinates. Okay. And then you're going to be seeing really why. So that's what answer your question. Why is it a covector? Okay. We're going to have another example later on in the course when we start talking about velocities and forces. Okay. This is a little bit of a teaser, okay, to show you that what we discussed so far abstractly, okay, actually has, you know, strong physical meaning and will come up later throughout the course. Yeah.
This potential function, I thought that you will discuss about the variational calculus or something like variation.
That's it. That's the gradient. Variational. You're thinking about variation. No, you're mixing variational with differential. No, that's something else. The variational calculus is something else. Variational calculus is related to functions. Yes, this is something else. This is just taking a function, taking differentiations of it, partial derivatives. That's it. So that's something else. So configuration space of a robot will be actually a manifold. If you look at one specific configuration for a robot, it will be a point on the manifold. Local coordinates, or what you call generalized coordinates of the robot, will actually be a chart representative. You know, degrees of freedom will be the dimension of the manifold. A motion or trajectory of the robot will be a curve on the manifold. The instantaneous velocity will be a vector in the vector space, in the tangent space. A generalized force on the robot will be actually a covector. The power that you know that you take to describe, you know, this force, so actually the pairing between these two. So power is just a scalar number, okay, between a vector and a covector. The velocity space, which is, you know, all of the q and q dots. Whenever if you have something that you see a q and a q dot, like a Lagrangian, for example, Lagrangian is always of q and q dot. You take the partial derivative of L with respect to q and partial derivative of L with respect to q dot to do the Euler-Lagrange equation. You're actually working on the tangent bundle. If you go to Hamiltonian mechanics, you're working on what's known as the phase space, where you start not working with q's and p's, not q's and q dots, but with the q's and the momenta. So q and p. So that's actually, you know, the cotangent bundle. If you have a Lyapunov function that's on the manifold, or some potential function that you want to describe, do control with, okay, you're looking at a function on the manifold. If you want to look at the gradient of this potential function, okay, to do control, as what we're going to be doing later on, you actually have a covector. And if you want to take just the v dot, okay, if you know what Lyapunov is, you know what the v dot should, how important it is, and it's simply just the pairing between this covector and the q dot, which is the vector. This doesn't make any sense It's just, you know, the trailer, okay, for the rest of the course. Yes.
And to continue on to the second derivative from the
Yes, we're going to be needing that. Actually, you're going to be introducing, this is related to what you know as the hashing. If you know the Jacobian, then it's related to the first derivative. The hashing is related to the second derivatives and so on. Yes, and it's also important in control. Not next class. We're not done yet. We still have many weeks.
Also, more than Lagrangian or something.
It's okay. Is it more advanced? Okay, that's a good question. Then it depends on who you're talking to. You can do stuff with Lagrangian. So in many cases they are equivalent. Okay, but it's just that when you write equations in the Hamiltonian or in the Lagrangian, they sometimes look completely different. And writing the equations is only the first thing we do. And when we do control, the first thing you do is just to write a model, which is just the equations that describe the physical system. But after that, you have the analysis, you have the simulation, you have the control. And some people just work in this way, some people work in that way. So is it more advanced? It depends on who you're talking to. But sometimes you can do nicer stuff. It's hard to say. It's just a flavor. At some point, they start to break down. Quantum mechanics, for example, you can only do it in the Hamiltonian approach, not in the Lagrange. General relativity, on the other hand, you can do it in the Lagrange, but not in the Hamiltonian. This is, where things start to break down. And it's completely irrelevant to you, but just, if you want to know more about that. Now, in the last few minutes, let's just look at some of the concepts, again, that we're going to be using later on, inshallah, in the course, which is the concept of matrix Lie groups. So let's go to the whiteboard. Remember, so let's just recall some definitions. What's the Lie group? A manifold that has a group structure. What is a group? Is a set with a binary operation. You give it two elements in the group, what do you get? Something in the group. So that's the closure, right? What else? You have associativity, you have the identity element, and you have the inverse that follows from that. What we're going to be doing later on is actually we're going to be working with manifolds that consist of matrices. The ones you know. We never talked about what matrices are. We never introduced something called matrices. We introduced something called vectors, but we never introduced something called matrices. Whenever I say matrices, this is what you know. Just putting numbers next to each other in an array. That's it. So what we're going to be doing later on is that we're going to have the same picture, manifold M, and we're going to have a point here. So P will be a point in M, but you also can think of it as some n by n matrix in your way. So that's what I mean here. So we're going to be working later on with manifolds that every point in it will be a matrix. No, not related to Schott. The manifold itself is matrices. No, there's no how. This is just. Let me remind you of another definition of the general linear group. Does anyone remember what the general linear group was? It was the set of invertible matrices. Exactly. We said that these anything inside, let's call them, M. And let's not use them because we already used that for the manifold. Let's use, you think of something. P, K. Okay, let's go for K. We use K for the field. Z. Okay, let's go for Z. Okay, so any Z in Rn times n that satisfies what? The determinant is not equal to 0, which means that it's invertible, right? Invertible matrices. GLNR actually is a manifold because you remember Rn times n? We said that Rn times n is isomorphic to what as a set? You remember? as a set was isomorphic to what? Rn squared, exactly. We said Rn squared on n times n, they are the same. The vectorization map, exactly. This vectorization map is actually a smooth map. And whatever we do for Rn to make it into a manifold, giving it the standard topology and all of the stuff that you do calculus with, you can actually give it to Rn times n. So in the end, we're going to actually, you can give this being a manifold because it's simply, it locally looks actually, it's locally a subset of Rn squared. So this is usually how what the manifold story goes for it. For you, it's just a manifold, but it's not just a manifold, because if we give it also this operation, what is this one? Matrix multiplication. So now we have GL and R with the matrix multiplication. It is what? It is a group. And we said we can make it into a manifold by inheriting, the structure from Rn squared. So now it's a group and a manifold, it is a Lie group. So in the end, this GLNR, now we can actually think of it as a Lie group. Okay. So this is GLNR as a Lie group. The GLNR will actually be an umbrella group. We're going to be more interested in actually stuff that's inside. And we're going to be working with them for the rest of the course a lot. For that, we're going to be introducing the notion of a matrix Lie group. So a matrix Lie group no, it's only for the multiplication. No. So matrix Lie group is simply any subset of GLNR. So we call G, if it's a subset of R, and it's also, that when you take the binary operation and you make it each two elements of G, you stay in G. Then we call this a matrix subgroup, okay? Or a matrix Lie group. Okay. So this is a matrix Lie group. Actually, GLN, by the way, you know what this symbol is? That this is subset and this is like something down. What does it mean? It can be GLN itself. So here, this actually means that G itself, what we're talking about, can be either all of GLNR or part of it. Okay. Okay. So this is what this symbol means. Okay, it's a proper subset. So now we have, if we have something like this, that's a subset of GLNR, and you have the group structure, you can talk about points on the manifold, you can talk about vectors, you can talk about covectors, maps between manifolds, and so on and so forth. Okay, so we can do all of this on this matrix Lie groups. And always keep in mind all of the points here. So if this is GL and R, or there's actually not GL and R, this is just G, which could be GL and R or any subset of it that's closed. And of course, exactly, all of the points here are matrices. So this point, let's call it, Z1. This point Z2. You have a curve between them. Z1 and Z2 are actually, they live in GL and R, which means they are invertible matrices. So Z lives in G actually implies that Z is an invertible matrix between quotes, what you call a matrix. And now, because we have, a curve, we can always talk about Z1 dot, for example, a tangent to that vector. Where does Z1 dot live? So Z dot lives in the tangent space to G, okay, at Z. Z1 or Z1 dot, so Zi dot. And here Zi. Okay, so the I here is just any point here on the manifold. Okay, we have infinite of these. Okay. If Zi looks like a matrix, what would Zi dot, what do you think it will look like? Another matrix, exactly. Same dimension. So if this will be an n times n matrix, this will also be another n by n matrix. What about covectors? That's a hard one, okay? But keep it in mind, okay? No, covectors will be something that eats a n by n matrix and spits out a scalar number. So a map that eats a vector and gives you a scalar number. What is the vector we're talking about here? What you call a matrix. So it's going to be eating a matrix and spitting out a number. That's it. Enough? Okay, I think enough. Okay. Let's stop here. Okay. This will be our umbrella. Okay, so this will be, the biggest, the set that has everything, the manifold that has everything we need to talk about. Inside of it, this is again just a teaser for you. Inside of it, we're actually gonna have many of subsets. One of them is called the orthogonal group. One of them is called the Euclidean group. Inside of here, there's actually one that's very important, which is called the special orthogonal group in n dimension. And inside of here, there's actually another one that's called the special, actually this will be n minus 1. This will be the special orthogonal group in n minus 1. Later on, starting from next lecture, inshallah, this is how we're going to be talking about rotations, rotation matrices, orientation of a robot, the attitude of a drone. The pose of an end effector will be here. If you want to talk about rotation and translation at the same time, it will be an element in here. We're going to be thinking about them as matrices. So we're going to be working with matrices a lot. But from now on, I'm pretty sure, okay, whenever you say matrix, first of all, you get shivers. So think twice before doing anything to these matrices, okay, because of all what we discussed, hopefully. That's the end of topic number 1. Hope to see you, inshallah, next lecture.